Hello, and welcome to our sensor instrumentation course. I'm Professor Nickolay Zosimovych from School of Robotics, and I'm excited to lead you on this journey over the next semester. And now, let's come to our main course description. Okay, so let's start this part. So, in this course, you will learn the field of mechatronics has, has broadened the scope of the traditional fields of electromechanics. Mechatronics is defined as the field of study involving the analysis, design, synthesis, and selection of systems that contribute electronic and mechanical components with modern control and microprocessors. So this module is designed to serve as a text for modern instrumentation and measurement course, a hybrid electrical and mechanical engineering course, replacing traditional circuit and instrumentation course, and a standalone mechatronics course, or the first course in a mechatronics sequence. So currently, many curricula do not include a mechatronic course, but include some of the elements in other more traditional courses. The purpose of a course is to provide a focused interdisciplinary experience for undergraduates that encompasses important elements from traditional courses as well as contemporary developments in electronics and computer control. These elements include measurement theory, electronic circuits, computer interfacing, sensors, actuators, and the design, analysis, and synthesis of mechatronic systems. This interdisciplinary approach is valuable to students because virtually every newly designed engineering product today is mechatronic system. Students from a wide variety of backgrounds may take this course. However, some basic knowledge of electrical circuits, like familiarity with concepts such as voltage, current, resistance, etc., is required. It's a minimum, maybe at school course, right? Furthermore, some basic familiarity with programming in any language is also required. Mastering the subject matter of sensors and instrumentation requires hands-on experience. So, and in this slide, you can see the course mark scheme, which contains two main parts in our university. But for another students who do not study in Xi'an Jiatong Liverpool University, it's not very interesting. So let's go on. And here you can see a recommended book, and it's only a few. And now I think we should to see a bit more videos for this step, okay? And just trying to find you about this video.
No plant is the same. They're all different. They have old equipment that was built in the 1920s all the way to brand new equipment that was built in the 2020s. And to effectively use the manufacturing analytics application, you have to be able to collect data from all of those machines. So over the last 5 years, we've been on the hunt for the perfect set of sensors to give us data from that old equipment all the way up to the new equipment, if you don't want to talk to the PLCs. And we settled on 4 different things. One is a photo eye. A photo eye is really good at counting things as it comes down a conveyor or it's ejected from a machine. We also have what we call a Swiss Army knife node that can pick up any combination of discrete or analog outputs on a machine. So we can use its existing sensors, existing electronics to pull data off of it. Another one is a temperature and vibration sensor, which put on a machine or a motor can tell us whether or not it's running just by its vibration signature. And then finally, our analog signals, things like current draw, temperature, vibration, humidity, tank levels, flow rates, that can tell us whether or not those machines are running as well.
Thanks for watching. And I think it's only as an introductory video, but maybe it's not enough quality for beginning, but I think I can resolve it a bit late. But now let's back to our main lecture course, okay? So, welcome to the Sensors and Instrumentation course. This is a fundamental and core concept today. So in this lecture, we will talk about mechatronics as the interface between actuators, sensors, and computers. All these elements you already listened just in a second before in introduction video, okay? So I'll be your instructor and guide as we explore the fantastic and really interesting and fun field of mechatronics together. Mechanical engineering as a widespread professional practice experienced a surge of growth during the early 19th century because it provides a necessary foundation for the rapid and successful development of the Industrial Revolution. The primary engineering disciplines of the 20th century, like mechanical, electrical, civil, and chemical, retain their individual bodies of knowledge, textbooks, and professional journals because the disciplines were viewed as having mutually exclusive intellectual and professional territory. We are now witnessing a new scientific and social revolution known as the information revolution, where engineering specialization ironically seemed to be simultaneously focusing and diversifying. This contemporary revolution was sprung by the engineering development of semiconductor electronics, which has driven an information and communication explosion that is transforming human life. To practice engineering today, we must understand new ways to process information and be able to utilize semiconductor electronics within our products, no matter what label we put on ourselves as practitioners, okay? Now, you see here before me a mechatronic device, which look like small robots. And we'll go ahead and explain you how it works. This is a simple robot arm that picks up a ball, twirls in around it, and this is what we call a hexapod robot. Not all that useful for anything besides entertainment. But one of the things you'll notice about this robot is that they have a few things in common. They have actuators in the form of servos, right? In the case of these two robots, they have sensors that help detect the position of the leg. Hands. They also importantly have computers, and these computers are special types of computers called microcontrollers that serve to detect what sensor trying to tell you, and then give commands to the actuators to do what the device needs. The term mechatronics is used to denote a rapidly developed interdisciplinary field of engineering dealing with the design of products whose function relies on the integration of mechanical and electronic components coordinated by a control architecture. Here's a rigorous definition of mechatronics. Mechatronics is the synergistic integration of mechanical engineering, electronics, and control theory in the design and implementation of machines. Mechatronic systems are sometimes referred to as a smart device. While the term smart is elusive in precise definition, in the engineering sense, we mean the inclusion of elements such as logic, feedback, and computation that in a complex design may appear to simulate human thinking process. Today, practically all mechanical devices include electronic components and some type of digital monitoring or control. Therefore, the term mechatronic system encompasses a myriad of devices and systems. Increasingly, microcontrollers are embedded in electromechanical devices, creating much more flexibility and control possibilities in system design. Examples of mechatronic systems include an aircraft flight control and navigation system, including those on consumer drones, automobile airbag safety system, and anti-lock brake system, right? Automatic manufacturing equipment, such as robots and numerically controlled NC machine tools, smart kitchen and home appliances, such as bread machines and clothes washing machines, and even toys, right? And this figure illustrates all the components in a typical mechatronic system. The actuator, and you can see here under the top, produce motion or cause some action. The sensors detect the state of the system parameters, input, output, and another digital device control system. Yet, as you can see here, provide connections between the control circuit and the input-output device. And final, we have a user interface that enables manual input and provide graphical displays or visual feedback to the user. The subsequent chapters of many books provided introduction to the elements listed in namely these block diagrams and describe aspects of their analysis and design. At the beginning of each chapter, the elements presented are emphasized in a copy of these figures. This slide. This will help you maintain a perspective of the importance of each element as you gradually build your capability to design your mechatronic system. This example describes a good example of mechatronic system, an office copy machine. All of the components in this slide, can be found in this common piece of office equipment. And now, let's go on. Measurement. A fundamental part of many mechatronic systems is a measurement system that composed of three basic parts illustrated in next figure. The transducer, from beginning, is a sensing element that converts a physical input into output. So a physical input on the left side, output on the right side. Usually, this is a voltage. And the signal processor performs filtering the amplification or other signal condition on the transducer output. The term sensor is often used to refer to the transducer or the combination of transducer and signal processor. Okay. Finally, a recorder. The recorder is an instrument of computer or an output device that stores or displays the sensor data for monitoring or subsequent processing. So these three building blocks of measurement systems come in many types with wide variation in cost and performance. It is important for designers and users of measurement systems to develop confidence in their use, to know their important characteristics and limitations, and to be able to select the best elements for the measurement task and hand. In addition to being an integral part of most mechatronic systems, a measurement system is often used as a standalone device to acquire data in laboratory or field environment. The following figure shows an example of measurement system. The thermocouple, as you can see in this part, is a transducer that converts temperature to a small voltage. And amplifier increases the magnitude to the voltage. And here AD, or analog to digital converter is a device that changes the analog signal to a coded digital signal. And the LED display, light emitting diode, displays the value of the temperature. And this design example deals with controlling the rotational speed of a direct current, DC. This figure illustrates the major components and interconnections in the system. The light emitting diode, LED, and you can see, as you can see in this on the top, provides a visual cue to the user that the microcontroller is running properly. The speed input device is a potentiometer. Potentiometer or port, which is a variable resistance. The resistance change as the users turn the knob on top of the port. The port can be wired to provide a voltage input. The voltage signal is applied to a microcontroller, basically a small computer on a single integrated circuit, to control a DC motor to rotate at a speed proportional to the voltage. Voltage signals are analog, but microcontrollers are digital. So we need to analog to digital, AD, and digital to analog converter in the system to allow us to communicate between the analog and digital components. Okay? Finally, because a motor can require significant current, we need a power amplifier to boost the voltage and source the necessary current. So, and here we can see some example of the power amplification speed control. We should notice that PIC microcontroller with the AD and external DA converter are not actually required, namely in this design. I just mentioned several seconds ago. Namely in this current port, the potentiometer voltage output could be attached directly to the power amp instead, producing the same functionality. So the reason for including the PIC with AD and the DA component is to show how these components can be interfaced within the analog system. This is useful to know in many applications. In addition, the design serves as a platform for further development, where the PIC can be used to implement feedback control and the user interface in a more complex design. An example where you might need the microcontroller is the loop in robotics or numerically controlled mills and lathes, where motors are often required to follow fairly complex motion profiles in response to inputs from sensors and user programming or from manual input. A transducer is an essential part of any information processing system that operates in more than one physical domain. These domains are characterized by the type of quantity that provides the carrier of the relevant information. Examples are the optical, electrical, magnetic, thermal, and mechanical domains. A transducer is that part of measurement system that converts information about the measures and from one domain to another, ideally without information loss. A transducer has at least one input and one output. In measuring instruments, where information processing is performed by electrical signals, either the output or the input is of electrical nature. Electrical nature, voltage, current, resistance, capacitance, and so on. Whereas the other is a non-electrical signal, like displacement, temperature, elasticity, and others. So, transducer with a non-electrical input is an input transducer, intending to convert a non-electrical quantity into electrical signal in order to measure that quantity. Okay? So, transducer with a non-electrical output, is called an output transducer, intended to convert an electrical signal into the non-electrical quantity in order to control that quantity. So, a more explicit definition of transducer is an electrical device that converts one form energy into another, with the scientific intention of preserving information. Okay? According to the common terminology, these transducers are also called sensor and actuator, respectively. So you can see here in this slide. So sensor is an input transducer and an actuator as an output transducer. It should be noted, however, that this terminology is not standardized. In literature, other definitions are found. Some authors make an explicit difference between a sensor and input transducer, stressing a distinction between the element that performs the physical conversion and the complete device, for instance, a strain gauge or transducer and a load cell of the sensor with one or more strain gauges and elastic element. So, transducer is a device used in measurement that provides an output quantity having a special relation to the input quantity. The same document defines a sensor as an element of measuring system that is directly affected by a phenomenon, body, or substance carrying a quantity to be measured. Modern sensors not only contain the converting element, but also part of the signal processing, analog processing, such as amplification and filtering, AD conversion, and digital processing. Many of such sensors have the electronics integrated with the transducer part on a single chip. Present-day sensors may have a bus-compatible output, implying full signal conditioning on board or include transmission electronics within the device, for instance, for biomedical applications. Signal conditioning may include to protect the sensor from being loaded or to reduce loading error, to match the sensor output range to the input range of the analog to digital converter, the enhance of the signal to noise ratio prior to further signal processing, to generate a digital bus-compatible electrical output, or transmit measurement data for wireless applications. In conclusion, the boundaries between sensor and transducer as proclaimed in many sensor textbooks, are disappearing or losing their fullness. The user buys and applies the sensor system as a single device with a non-electrical input and an electrical output, like analog signal or microprocessor compatible digital signal or radio signal. Sensors play an important role not only in mechatronics, but also in many other areas. They are widely applied nowadays in all kinds of industrial products and systems. A few examples are as follows: consumer electronics, household products, public transport, automotive, process industry, manufacturing, production, agriculture and breeding industry, medical instruments, and many other areas where the introduction of sensors has increased dramatically the performance of instruments, machines, and products. The world sensor market is still growing substantially. The worldwide sensor market offers over 100,000 different types of sensors. And this figure not only illustrates the wide range of sensors used, but also the fact that selecting the right sensor for a particular application is not a trivial task. Reasons for increasing interest in sensors are as follows. And first of all, it's reduced price. The price of sensor not only depends on the technology, but also on production volume. Today, the price of a sensor runs from several 10,000 or euros for single pieces down over a few euro cents for 100 million volume. Another interesting function, miniaturization. The IC-compatible technology and progress in micromachining technology are responsible for this trend. Pressure sensors belong to the first candidate for realization in silicon from the early 1960s. Microelectromechanical systems are gradually taking over many traditionally designed mechanical sensors. Nowadays, solid-state sensors in silicon or compatible technology for almost every quantity are available, and there is still room for innovation in this area. Smart sensing. The same technology allows the integration of signal processing and sensing functions on a single chip. Special technology permits the processing of both analog and digital signals, or so-called mixed signals, resulting in sensor modules with microprocessor-compatible digital output. Popular MEMS, micro electromechanical systems, sensors are accelerometer and gyroscope. On the left, you can see the accelerometer and gyroscope on the right side. So the MEMS accelerometer can be made completely out of silicon, only using micromachining technology. The seismic mass is connected to the substance by thin, flexible beams acting as a spring. The moments of the mass can be measured by, for instance, integrated piezoresistor positioning on the beam at a location with maximum deformation or by a capacitive method. In mechatronics, mainly sensors for the measurement of mechanical quantities are encountered. The most frequent sensors are for displacement, means for position, and force, like pressure. But many other sensor types can be found in a mechatronic system. Many sensors are commercially available and can be added to or integrated into mechatronic systems. This approach is preferred for systems with relatively simple tasks and operating in a well-defined environment as commonly encountered in industrial applications. However, For more versatile tasks and specific applications, dedicated sensor systems are required, which are often not available. Special design, further development, or even research are needed to fulfill specific requirements. For instance, with respect to dimensions, weight, temperature range, and radiation hardness. In this course, we follow a strict categorization of sensors according to their main physical principles. The reason for this choice is that sensor performance is mainly determined by the physics of the underlying principle of operation. For example, a position sensor can be realized using resistive, capacitive, inductive, acoustic, and optical methods. The sensor characteristics are strongly related to the respective physical transduction process. However, a magnetic sensor of a particular type could be applied as, for instance, a displacement sensor, a velocity sensor, or a tactile sensor. For all these applications, the performance is limited by the physics of these magnetic sensors. Apparently, position and movement lead the list of measurement quantities. Common parlance contains many other words for position parameters. Often transducers are named after this word. Here is a short description of some of these transducers. Transducers for the measurement of force and related quantities are as follows. Many transducers have been given names according to their operating principle, construction, or a particular property. Examples are as follows. Some sensors use a concatenation of transduction steps. A displacement sensor combined with a spring can be act as a force sensor. In combination with a calibrated mass, a displacement sensor can serve as an accelerometer. The performance of such transducers not only depend on the primary sensor, but also on added components. In the examples about the spring compliance and the seismic master spectrum. Information about a particular quantity can also be obtained by calculation using relations between quantities. The accuracy of the result depends not on the errors in the quantity that are measured directly, but also on the accuracy of the parameters in the model that describe the relation between the quantities involved. For instance, in an acoustic distance measurement, the distance is calculated for the measured time of light, T of R, with associated error, and the sound velocity. And accurate measurement results required knowledge of the acoustic velocity of the medium and the prevailing temperature. Some variables can be derived from the others by electronic signal processing. Speed and acceleration can be measured using a displacement sensor by differentiating its output and signal once or twice, respectively. Conversely, by integrating the output signal of an accelerometer, a velocity signal is obtained, and by a second integration, a position signal. Obviously, the performance of the final result depends on the quality of the signal processing. The main problem with differentiation is the increased noise level, in particular, in the higher frequency range. An integration may result in large drift due to the integration of offset. According to the amount of information, a sensor or sensing system offers three groups of sensors and can be distinguished: binary sensors, analog sensors, and image sensors. Binary sensors give only one bit of information, but are very useful in mechatronics. They are utilized as and stops, as even detectors as a safety device. Depending on their output, 0 or 1, process can be started, terminated, or interrupted. The binary nature of the output makes them highly intensive to electrical interference. Analog sensors are used for acquisition of metric information with respect to quantity related to distance, like pressure, gripping force, and bend, or other, like thermal, optical, mechanical, electrical, or magnetic properties of an object. A wide variety of industrial sensors for this purpose are available. The third category comprises image sensors intended for the acquisition of information related to structures and shapes. Depending on the application, the sensor data refer to 1, 2, or 3-dimensional images. The accuracy requirements are less severe compared to the sensor from the preceding category, but the information content of the output is much larger. As a consequence, the data acquisition and processing for such sensors are more complex and more time-consuming. The next section presents some general aspects of sensors, following the categorization in binary, analog, and image sensors, as introduced before. Actually, the section serves as a general overview of the sensor and sensing systems, which are discussed in more detail in subsequent lectures. Details on physical background, specifications, and typical applications are left for those lectures. Here, the differences in approach are highlighted and their consequences for applicability in mechatronic systems are emphasized. A binary sensor has an analog input and two-state output. Two-state means 0 or 1. Okay? It converts the analog input quantity to a 1-bit output signal. These sensors are also referred to as switches or detectors. They have a fixed or an adjustable threshold level X. So you can see in horizontal line in figure A. In fact, there are essentially two levels making the hysteresis interval, as you can see here in figure B, hysteresis interval. Any analog sensor can be converted to a binary sensor by adding a Schmidt trigger or comparator with hysteresis. So this Schmidt trigger is comparator that contains, namely, this sort of hysteresis. Also, hysteresis lowers the accuracy of the threshold detection down of the hysteresis interval, like here, drawing input. It may help reducing unwanted bouncing due to the noise in the input signal. Most binary sensors measure position. Binary displacement sensors are also referred to as a proximity sensor. They react when a system part or a moving object has reached a specified position. Two major types of the mechanically and magnetically controlled switches. Mechanically controlled switches are actually touch sensors. They are available in a large variety of sizes and construction. Sorry, my PC is a low battery. I should improve it. Let's go. So, for special conditions, there are waterproof and explosion-proof types. For precision measurement, there are switches with an accuracy less than ±1 micrometer, and a hysteresis interval in the same order, guaranteed over a temperature range from -20 centigrade up to 75 plus 75 centigrade. Another important parameter of a switch is the reliability, expressed in the minimum number of communications. Mechanical switches have a reliability of about 10 in power 6. A reed switch is a magnetically controlled switch. Two magnetizable tongues or reeds in a hermetically closed encapsulation filled with an inner gap. The switch is normally off. It can be switched on mechanically by permanent magnet approaching the sensor. Reed switches have good reliability, over 10 communication at switching frequency of 50 Hz. A disadvantage is the bouncing effect, the chattering of the contact during a transaction of state. Reed switches are applied in various commercial systems, from cars monitoring broken lights, level indicators, to electronic organs like plane contact, to telecommunication devices and testing and measurement equipment. In mechatronic systems, they act as an end of motion detector, touch sensors, and other safety devices. The technical aspects are described in later lectures on inductive and magnetic sensors. The drawback of all mechanical switches are a relatively large switch on time. For each switching typically is 0.2 microseconds and back. This explains the growing popularity of electronic switches, such as optically controlled semiconductors and cold plates. There is a wide range of binary displacement sensors on the market for a variety of distances and performance. And this table presents a concise overview of specifications. All the sensors, except for the mechanical switch, operate essentially contact-free. Obviously, the optical types have the widest distance range. The optical inductive and capacitive types are essentially analog sensors with adjustable threshold levels. The specifications include interference and the readout electronics. In particular, the response time of the sensors itself may be much better than the value listed in the table that you can see a second before. Accuracy data include hysteresis and apply for the whole temperature range. Maximum operating temperature range near the plus 70 centigrade difficulty. There is an overwhelming number of analog sensors on the market for almost any physical quantity and operating according to a diversity of physical principles. In mechatronics, the major measurement quantities of interest are linear and angular displacement, their time derivatives, velocity and acceleration, and force, including torque and pressure. Imaging is a powerful method to obtain information about geometrical parameters of objects with a complex shape. The 3D object or a complete scene is transformed to a set of data points representing the geometrical parameters that describe particular characteristics of the object. For instance, its pose, position, and orientation in the space, dimensions, shape, or identity. An essential condition in imaging is the preservation of the required information. This is certainly not trivial. Photographic and camera pictures are 2D representations of a 3D world, and hence much information is lost by the imaging process. Three basic concepts for the image acquisition are depicted schematically in these and next two figures. In the first method, the scene of to be imaged is scanned point by some mechanical means, like a mirror or a stepping motor, right? Or electronically, for instance, with phase array. Such an imaging system is often referred to as a range finder. It yields distance information over an angular range determined by the limits of the scanning mechanism. The output is a sequential data stream containing 3D information about the scene, depth data from the scanning sensor, and angular data from the scanning mechanism. Also, the data points are three-dimensional. Information is obtained only about the surface boundary range and not that part of the surface that is connected to the sensor system by a line of different sizes. Therefore, range data are sometimes called 2.5D data. In Figure A, on the left side of this slide, the sensor and scanning mechanism are presented as a single device. For most scanning systems consist of several parts, for instance, a fixed transmitter and receiver, and one or more rotating mirror or reflector. Sometimes the transmitter, the receiver, or both are mounted on the scanning device. Although the scanning method is slow, it requires only a single sensor, which can therefore be of a high quality, right? In the second method, in this Figure B, the scene is scanned line by line. Vertically, you can see here, again, using some mechanical scanning device. Each line is projected on an array of sensors. In the optical domain, for instance, a diode array. The sensor array may include electronic scanning to process the data in a proper way. Nevertheless, the mechanical scanning mechanism operates in only one direction, which increases the speed of image formation and lowers construction complexity as compared to point-wise scanning. The third method in this Figure C involves the projection of the unknown image on a 2D matrix of point sensors. This matrix is electronically scanned for serial processing of the data. Since all scanning is performed in the electronic domain, the acquisition time is short. The best known imaging device is the CCD matrix camera, charge coupled device, CCD. It has the highest spatial resolution for raw matrix images. Considering the nature of the various possible information carriers, there are at least three candidates for image acquisition: light, ultrasound, and contact force. All three are being used in both scanning and projection mode. Most popular is the CCD camera as imager for exploring and analyzing the workspace of a mechatronic system or a robot's environment. However, in numerous applications, the camera is certainly not the best choice. The acquisition of an image is just the first step in getting the required information. Data processing is another important item. There is a striking difference between camera-based vision and non-vision data processing. The main problem of the CCD camera is the provision of superfluous data. The first step in image processing is, therefore, to get rid of all irrelevant data in the image. For instance, a mere contour might be sufficient for proper object identification. The point is how to find the right contour. However, most non-vision images suffer from a too low resolution. Here, the main problem is the extraction of information from the low resolution image, and in the case of scanning system, from other sensors. In all cases, modern-driven data processing is required to be able to arrive at proper conclusions about features of the object or the scene under test. Most optical imaging systems applied in mechatronics and robotics use a camera, CCD type, or CMOS. and a proper illumination of the scene. The image, or a pair of images, or even a sequence when 3D information is required, is analyzed by some image processing algorithm applied to the intensity and color distribution in the image. Particular object features are extracted from particular patterns in light intensity in the image. Position information is derived from the position of features in the image, together with camera parameters, position and orientation, or maybe focal length. Specified conditions for getting a proper image must be fulfilled. An illumination that yields adequate contrast and no distributing shadow, and a camera setup with a full view of the object or the scene, and with a camera that has a sufficiently high resolution, so as not to lose relevant details, right? Obviously, a 2D image shows only a certain prospect of the object, never a complete view or self-occlusion. In case of more than one object, some of them could be sometimes partially hidden behind other occlusions, a situation that makes the identification much more difficult. Even in the most favorable situation, the image alone does not reveal enough information for the specified task. Besides a proper model of the object, we need a model of the imaging process, position and orientation of the camera parameters like focal length and the position of the light source with respect of the object and color. All of these items determine the quality of the image from which features are to be extracted. The pose of the object in the scene can be derived from the available information and knowledge of the imaging system. Many algorithms have been developed to extract useful features from an image that is built up of thousands of samples in space and time, described by color parameters, gray tone values, or just beats for black and white in images. The image is searched for particular combinations of adjacent pixels such as edges from which regions boundaries are derived. Noise in the image may disturb this process, and special algorithms have been developed to reduce its influence. The result is an image that reveals at least some characteristics of the object. For further information on feature extraction, the reader or any other students you may find on the literature on computer vision and image processing. The interest in acoustic waves for imaging is steadily growing, mainly because of the low cost and simple construction of acoustic transducers. The suitability of acoustic imaging has been provided in medical, geological, and submarine applications. Applications in mechatronics have, however, some severe limitations, going back to ultrasonic wave propagation in air, where most mechatronic systems operate. Despite these limitations, many attempts have been made to improve the accuracy and applicability of acoustic measurement systems. In particular, as they are applied to distance measurement and range finding. The most striking drawback of acoustic imaging is the low spatial resolution due to the diverging beam of acoustic transducers. The directivity of the transducers can be improved by increasing the ratio between the diameter of the wavelength. Even at medium frequencies near the 40 kHz, this results in a rather large device. An alternative method is the use of an array of simultaneously active acoustic elements. It's going to be narrow. Further, the direction of this beam can be electronically controlled by variation of the phase shift or time delay between the elements of array. This technique, known as a phased array, applies to transmitters as well as receivers. Instead of geometrical model for use in object recognition, other models might be used. An example of such a different approach is shown schematically in this slide. An acoustic signal, the stimulus, is transmitted toward the object. So you can see generator and acoustic is transmitted to the stimulus, to the object. And the shape of echo patterns, that's responded, yes, and this one, is transmitted toward the object. As this shape determined by the object shape and orientation. In a learning phase, echo patterns of all possible objects are stored in computer memory. They can be considered acoustical signatures of the object. The echo pattern from a test object belonging to the trained set is matched to each of the stored signals. Using a minimum distance criterion reveals the best candidate. Evidently, the test conditions should be the same as during the learning phase. A fixed geometry and a stable stimulus are required. The comparison process may be performed either in the frequency domain or in the time domain. With this simple technique, it is possible to distinguish between objects whose shapes or orientations, normal versus upside down position, are quite different. With an adaptive stimulus and suitable algorithm, even small defects in an object can be detected by ultrasonic techniques. So the method so often used in modern medicine. Under certain conditions, very small object differences can be detected, for instance, between sides of a coin. In contrast to optical and acoustic imaging, tactile imaging is performed by mechanical contact between sensor and object. Making contact has advantages as well as disadvantages. Disadvantages are the mechanical load of the object. It may move or be pressed, and the necessity of moving the sensor actively towards the object. Advantages of tactile imaging include the possibility of acquiring force-related information. For instance, touching force and torque, and mechanical properties of the object, like elasticity, resilience, and surface texture. Another advantage over optical imaging is the insensitivity to environmental conditions. This versatility of a tactile sensor makes it very attractive for control purposes, especially in assembly process. Moreover, tactile and vision data can be fused to benefit from both modalities. In robotics, tactile imaging is mostly combined with the gripping action. For inline control, the tactile sensor should be incorporated into the gripper of the robot, allowing simultaneously force distribution and position measurement during the motion of the gripper. And this permits continuous force control as well as position correction. In inspection systems, like coordinate measuring machine, the object under test is scanned mechanically by a motion mechanism, with a touch sensor as an effector. You can see in the top part of this picture. The machine is controlled to follow a path along the object, while keeping the touch force at a constant value. Position data follow from back transformation of the tip of sensor coordinates to work coordinates. The scanning is slow, but can be very accurate, down to 10 nanometers in 3 dimensions. Next lecture will be selection of sensors. I hope you enjoyed this lecture, and I'm looking forward to see you next time. See you next time. Bye.